So good evening, everyone. I welcome you all to the sixth lecture of the STEMS 2022 lecture series. Today, we are quite excited and delighted to have Professor Ryan O'Donnell with us. I'm sure you all know him, but allow me to introduce. He is a professor of Theory Group, Computer Science Department at CME. His research interests are in quantum computation, complexity theory, analysis of Boolean functions, approximability of optimization problems, and several other vast topics. Professor Ryan completed his PhD from the prestigious MIT under the guidance of Professor Madhusudan. Today, he will be talking on a fascinating topic, the advantages of quantum computing. Before we begin, a couple of points. It would be great if people could turn on their videos so we can reach closer to an in-person talk, which we have been missing for a long time. And also, if you have any questions, please put them in the chat and the moderators will voice over at the appropriate time. Without further delay, I invite Professor Ryan O'Donnell. I hope all of you enjoyed our talk, Professor.
All right, thanks so much. Thanks so much for inviting me. It's great to be here virtually with you. And as mentioned, I'm going to tell you a little bit about quantum computing. I'm not going to tell you everything about it, just what quantum computing you can do with 1 qubit. So let's get started. So I'm here in Pittsburgh. It's in the northeast part of the United States. So here's a map, and I teach at Carnegie Mellon University. It's a nice place. Hope you can visit sometime. Yeah, it's even got like 4.7 stars on Google Maps review. And I guess here over there, mostly in Chennai, which is I'm sure a lovely place. I would love to visit it sometime. And take a look. It's even better. It's 4.8 stars. So I really got to make it at some point. Actually, I'm not originally from Pittsburgh. I'm originally from some town that's near Toronto. This gray line here is the border between Canada and the United States. So in fact, I'm a Canadian person. My home is Canada. And I'll tell you one thing about Canada. We have this very good-looking prime minister. It's not this person. It's also not Sophie. It's this guy over here. Justin Trudeau is his name. Here's another photo of him. And a few years back, he was giving a press conference. This is here. He's looking like very much like a prime minister, you know, in a suit. Oops. Yeah. Here we go. At the Perimeter Institute, which is some university research institute in Southern Ontario, where they do physics and quantum computing, among other places. And he was taking a press conference. It wasn't about, you know, the university or anything. It was just a regular old press conference. He was there. So I'll play you a little clip from it. The first voice you'll hear is like the off-screen reporter asking the prime minister a question. So hopefully the sound comes through okay.
I was going to ask you to explain quantum computing, but when do you expect Canada's ISIL mission to begin again? And are we not doing anything in the interim while we prepare?
Okay. Very simply, normal computers work by... Don't interrupt me. When you walk out of here, you will know more. Well, no, some of you will know far less about quantum computing, but most of you, normal computers work either there's power going through a wire or not. It's 1 or a 0. They're binary systems. What quantum states allow for is much more complex information to be encoded into a single bit. Regular computer bit is either a 1 or a 0, on or off. A quantum state can be much more complex than that because, as we know, things can be both particle and wave at the same times, and the uncertainty around quantum states allows us to encode more information into a much smaller computer. So that's what's exciting about quantum computing, and that's what we're doing. Don't get me going on this, or we'll be here all day, trust me.
Yeah, me too. I love quantum computing. I could be here all day as well. So there you go. That's the prime minister telling us about quantum computing. Not bad. I give it like a B+ as the level of explanation. So we'll get into it a little bit just now and see what exactly is the deal with this. Okay, so as the prime minister said, we have our normal computers, or classical computers, we sometimes call them. Classical just means not quantum. And indeed, it's a binary system. I mean, everything is digital, as you know. Computers, they work with bits, zeros and ones. Again, bits are like a logical concept, like a mathematical concept, okay? So an abstraction. But computers are like physical objects that exist in the real world, okay? So when you want to use a computer, to do computation on bits, you need to physically represent the bit somehow. And as Trudeau mentioned, you can do this in a variety of ways. A common way with like circuits is you have a wire and it's got some voltage on it, which is somehow comes from electrons. And you say that, okay, the physical property of having low voltage will correspond to the logical 0 and high voltage will correspond to 1. Okay. Or if you have like a hard drive, I guess these days, most hard drives, they have like billions of like magnetized regions or potentially magnetized regions. And if the region is magnetized, that's a 1. And if it's unmagnetized, that's a 0. Okay, so this is how you store logical bits with physical bits on a computer. Now, you don't want to just store them. I mean, in order to do computing, you need to know what they are. So you need to like read them out or find out what they are. So if you're storing your bits logically or physically with voltage on a wire, then maybe you got some like voltmeter and you can connect it and you can find out what the bit is supposed to be. Or you can translate this like physical property into a logical, mathematical.
Ryan, you seem to have been muted. Hello, Professor. Can you?
Yeah, sorry. I got a message saying the host has muted you, but like I guess it's back to normal.
Yeah, it's back to normal.
Okay, great, cool.
Sorry for the trouble.
Great. All right. So, okay, so that's when you're storing logical bits on a regular computer, and if you think about it, like a magnetized region or a wire, it's actually kind of storing this voltage with like millions of electrons. Let's say for the electric current version. Now we're trying to miniaturize everything in life, and so at the quantum scale, you might try to represent a physical, a logical bit with like maybe one physical particle or a very small number of physical particles. So this is taking us to the quantum scale. So for example, maybe you have an electron. I don't know how to draw an electron, so this is an electron. And an electron has a property called spin, and it can be either spin up or spin down. And what that really means, it's hard to say, but the physicists say it has this property. And so you could say, great, okay, if it's spin up, I'll make that correspond to 0, and spin down corresponds to 1. And now I've got a bit stored potentially with like one physical object. Okay, another way you could do it, I mean, you can do this in a wide variety of ways. You just need like some particle or atom or something that can have one of two properties, and then you could use those properties potentially to store a bit of information. So if you have maybe a photon, it has a variety of properties, including a property called polarization, and it can be either, the photon's traveling, it can be wiggling like this or wiggling like that, and it's called polarization. And so it can be either horizontally polarized or vertically polarized. And, you can try to use this in computation and, treat horizontal as 0 and vertical as 1. And great, now you have some other way of representing bits. Okay, so again, we need to be able to measure this property of the particle we're using to try to encode a bit, and in order to find out if it's 0 or 1. And in the case of like electron spin, you can do it in a very complicated way. I got this diagram off Wikipedia. You like put the electron through like a giant magnet. And actually, if it's spin up, that causes it to move like physically upwards. And if it's spin down, it causes it to move physically downward. So you've actually converted this spin property to a different binary property like position, whether the electron is up here or down here. And then I guess there are physical devices that can tell you where the electron is. So maybe it's a little complicated to measure the spin of a physical bit of an electron. Actually, this is why I prefer photons. Now, photons are actually not used much in quantum computers for various reasons, but I use them a lot because I can understand them. Because actually, this property of polarization is like maybe something that you've actually like literally encountered in your life. Because, for example, if you want to like measure or detect the polarization of a photon, you can use like a fabulous device known as like a pair of polarizing sunglasses. Okay, which are these sunglasses you buy at the store if you like drive a lot and don't want to get glare, that change like how much light is let through, and I'll talk about it in a minute, based on the polarization property of the photons. Okay, and so this is like an actual real world way to measure this property of single photons. In fact, you may also encounter this if you go to like a 3D movie. You see these people here, they're wearing these like 3D glasses. And these are literally just like, super cheap pieces of plastic they put in the glasses. And they set it up so that, they play an image with horizontally polarized photons, and those can only go through one side of the glasses. And they play a different image, slightly different, with vertically polarized photons, and those only go through the other side of the glasses, and then your eyes see two different images, and so it looks 3D. Okay, so I like polarization because, you know, it's like some physical thing that can think about in real life. Okay, and in fact, this is not expensive. Like, you can go to like the store and buy like this piece of plastic that's a whole polarizing filter, like in the 3D glasses for, okay, this is $8 US. I translated this is like 600 rupees, which is not even that expensive because this is actually a pack of 10. So like one of these little pieces of plastic costs like 60 rupees. So that's negligible. So great. So you can buy a 60 rupee piece of plastic and get a polarizing filter that actually lets you detect the polarization state of photons, which is pretty cool. Now, in the rest of the talk, I'm going to draw this not as like the actual black or gray square, but this is like a diagram. This circular thing is going to represent for me what's called a horizontally polarizing filter. Okay, so this is like 60 rupee piece of plastic that you can buy. And how does it work? Well, if you have a photon and it's horizontally polarized, if you send it through this horizontally polarizing filter, like it just goes through, like nothing happens, everything is fine. On the other hand, if you have a photon that's vertically polarized and it hits a horizontally polarizing filter, then it doesn't get passed through, it gets blocked, and maybe I guess it gets transformed into a tiny amount of heat. Okay, so this is how the 3D glasses work. This will let through, the horizontal filter only lets through the photons that are horizontally polarized. Now, for the other lens, you need a vertically polarizing filter, and you don't even need to spend like another 60 rupees to get it. You can actually make it just by physically turning this piece of plastic 90 degrees. And now it's a vertically polarizing filter. I guess you need 120 rupees if you need one for each eye. Right, so this has a very similar properties as you might guess. If you have this vertically polarizing filter and you pass a vertically polarized photon through it, then it'll just pass through. And if you pass like a horizontally polarized photon through it, it'll get blocked and somehow converted to heat. Okay, cool. So in this way, you can measure the polarization of a photon. In fact, there's a cool experiment you can do to check this like a polarization property. You can get out like a regular old lamp and one of these little pieces of plastic, and you shine the lamp at the piece of plastic and you look through it. And you'll find that like about 50% of the light comes through to your eye. So it looks kind of gray. And roughly speaking, this is not quite right, but like you can think of like the incoming light as being like randomly 0 or 1. It's just sort of, there's no special property. And so about half of the photons are able to get through, and that's why it's 50% intensity. Okay, but now all the ones that are coming through are definitely horizontally polarized. So now if you put a vertically polarized filter in front of that, then, by these properties, they're all blocked. It's 100% blocked. Okay, and then 0% light intensity comes through. So you take these two pieces of plastic and, it's kind of gray if you shine it to a light, and you put the other one, and it's like the 90-degree orientation, and it's perfectly black. I'm getting to quantum computing, by the way. We'll be there in a second. In fact, one thing I couldn't help but adding here, I won't explain why this works, but it is due to quantum. There's an additional party trick you can do if you spend 60 more rupees. If you take a third polarizing filter and rotate it 45 degrees and put it in between this vertical and horizontal filter, then actually suddenly light gets through, which is weird, right? With just the two filters, like no light gets through. Then you interpose in between like a third object. Surely this should only block the light even more. But no, somehow this causes light to get through. I actually experimented with doing it with like actually the plastics in front of the camera for my video camera, but it didn't work so great. So you just have to try it yourself at home. I won't actually explain why this is true. You can think about it, but we're going to get into exactly this issue of maybe things that are neither horizontal nor vertical in the next few slides of the talk. Okay, so actually, I even think of like a, oh, sorry. I see I'm looking in the chat here. Oh, this is about the old internet connection issue. Okay, I'll try to keep an eye on the chat at the same time. So I actually don't even think the filter is like the most direct way of trying to measure if a photon is representing 0 or 1. You can also build like a device that's just called like a polarization measuring device. And it's probably not actually looking like a camera, but I've depicted it as a camera connected by a wire to like an LCD readout screen. And in general, whenever you have like a physical object that can have one of two states, you can build a physical measuring device that like takes in that object and outputs, let's say 0 or 1 on the screen, depending on which of the two states it's in. Okay, so the way this thing works is if you put in a horizontally polarized photon, then it just reads out 0 on the screen. And if you put in a vertically polarized photon, then it reads out 1 on the LCD screen. Okay, so it just tells you the polarization state of the photon. Actually, you may have noticed all along, I didn't mention it, but like instead of writing 0 and 1 in the normal way, I wrote them in these like bizarro asymmetric brackets. And this is a convention from quantum computing, quantum mechanics that actually it's a good convention, it'll make sense, but I'll explain a little bit about it later. Anyway, it just means 0 and 1 for now. Okay, so I'm actually a computer scientist, and we're gonna talk about quantum computing. So I think of this almost like, I wanna think of it a little bit as like, a programming language code thing. This physical object lets you implement the measuring operation on a qubit or on a bit. And so I think of actually a horizontal filter as being a little bit more of like a composite object. Horizontal filter at a high level, it doesn't do this literally physically, but at a high level, you can think of it as, it takes in a bit, and then it does this measurement operation to it, and it gets the readout, whether it was 0 or 1, horizontal or vertical. And then it takes 2 different actions depending on whether it was 0 or 1. So if it read out that it was 0, horizontal, then it just returns it to you, like it passes it through the filter. And if it read out that it was 1, then it like doesn't pass it through to you, and it just converts it to heat. Okay, so you can also think of the vertical filter as doing basically the same thing, except it reverses this like if then else condition. Okay, cool. So I mean, still haven't really got to quantum, but I've sort of told you how you could try to do computation where you represent all your bits with like photon polarization. Well, there's still one more thing you would like to do. If you have bits and you're trying to do computing, you don't just like set them up and then read out what they are. You need to manipulate them. This is what computation actually is. So for example, you would like to be able to take a bit and maybe do the logical NOT operation on it, convert 0 to 1. This is sort of like the actual computation part. And again, like if you're representing your bits with some, electron spin or something, then I don't even know exactly how you do it. But like if it's polarization of a photon, you can do it in a real simple way. You just need to get like a piece of kind of translucent material, like apparently like quartz is good for this. And that's it. You would get like a slab of quartz and you blast the photon through it. And it kind of will act like a NOT gate if you get the thickness of the piece of quartz just right. Okay, so if you get just the right thickness of quartz, then like when you pass a horizontally polarized photon through it, then that will change its polarization status to vertical. Okay, so as I said, now we can manipulate 1 bit and we can measure 1 bit. But you can't really build a computer with just 1 bit, right? There's no real interesting computation you can do on a computer with like a single bit of memory. But sort of the point of this talk is that you actually can do some interesting computation if you only have 1 qubit. So we're going to now talk about quantum bits, which are called qubits. And now you can actually do some really, really cool computation with 1 qubit, but you can do some cool stuff. So this is what I want to tell you about today. Not full-fledged quantum computing, just quantum computing with 1 qubit. So, I mentioned that, if you get this thickness of this slab of quartz or whatever just right, it will implement like the NOT operation. It'll like convert 0 to 1. But what if you don't get it right? What if you take the slab and just like shave it so it's like half the thickness? Then what does it do? I mean, it's existing in physical reality. You can put the photon through. What happens? Well, if you make it half as thick, then what happens is the polarization when it gets through looks like this. And this is not vertical or horizontal, but it can happen. Now, what they'll tell you is that, this is now, you should think of it as a qubit because it's neither 0 nor 1. It's like a superposition of 0 and 1. It's like an equal combination of 0 and 1, which, once you first hear about this in quantum computing, it sounds very mysterious. Like, how could you have something that's like both 0 and 1? But actually, in the context of like photon polarization, it doesn't seem particularly mysterious at all, right? I told you a photon as it travels can be wiggling horizontally, or it can be wiggling vertically, and those are 0 or 1. It doesn't take a lot to imagine that it could also wiggle like in a diagonal fashion like this. And okay, that's the status of it. So it's a bit less mysterious. It actually becomes more mysterious when you're representing your logical bits by a physical property of a particle, which is not polarization. For example, it's possible for an electron to have some kind of superposition of upspin and downspin. And you might say like, okay, sure. But another binary property that a particle can have is like physical location. Like the particle can either be here or here. That's actually what happens if you put the electron with the spin through that magnet. It either goes here, it's either here or here. And there's another binary property, and it's a property of every particle or particle system in nature, that if it can have one of two properties, or one of two basic states, then it can also be in a superposition of those states. And this maybe seems a lot more weird, to imagine that a particle can be in some kind of superposition of being like over here and being over here. And that's totally true. It can also be in a superposition of locations. But this is another reason, like when I first talk about quantum computing, I like to talk about photon and polarization, because it seems like a little less wacky to imagine that, like, okay, it's some combination of horizontal and vertical polarization. Okay, so let me tell you a little bit about one quantum bit, or qubits. So in fact, qubits has the property that it's not necessarily just 0 or 1. It can be some kind of combination of 0 and 1, or superposition. So in general, a logical qubit is expressed like this. It's sort of like x amount of 0 plus y amount of 1. These amounts are sometimes called amplitudes, but maybe I'll just call them amounts. And what are x and y? They're just real numbers. Now, it's mathematically best, maybe correct to say they're not any old real numbers. They're real numbers that have the property that x squared plus y squared equals 1. So maybe that's one less degree of freedom than you thought, but it's still, infinitely many possibilities for x and y. I'll answer the question from the chat in just a second. Technically, I mean, if you're in the know, you may know that actually these amounts x and y can even be complex numbers, but I put it real teeny tiny on the slide because just never mind about that. Just imagine them as real numbers. So this is all the possible states of a qubit. They look like this. There's a question in the chat from Bamidi. How do you manufacture qubits whose state is equal superposition? Well, in fact, we just did it right here. This photon here, okay, depicted, is an equal superposition of 0 and 1. It's just because you've chosen to decide to call horizontal 0 and vertical 1, and therefore, if you have this diagonal polarization, then it's an equal combination of 0 and 1. And you can get it by, maybe getting a horizontally polarized photon, which maybe you got by passing a bunch of photons through a horizontal filter and waiting for one to come out, and then putting it through this slab of quartz. Now, it's true in general, like this is the physical, machine, if you will, that can take a 0 qubit and turn it into an equal superposition of 0, 1 when you're storing your logical qubits with polarization of light. If you're storing them in a different way, like the spin of an electron, then I don't even know exactly what you do. For some implementations of quantum bits, you fire a laser at the object for a while and or maybe you put it into some magnet. So it depends exactly on how you're storing physically your logical qubit. But for this polarization, it's kind of not too hard. So particularly this, with this setup, this equal combination of 0 and 1 looks like this. X is square root of a half, and y also is square root of a half. These are equal, and their squares add up to 1. So this is the sort of mathematical representation of this particular qubit. And so you can see actually for if you have one qubit, it has some x amount and y amount, and the squares add up to 1. So it's very logical to plot its state, in the xy plane, and every possible state will lie on this unit circle. This circle represents all the points where x squared plus y squared equals 1. So for example, a possible qubit state, which is different from the one we saw, this point might be x equals 0.8 and y equals 0.6, because 0.64 plus 0.36 adds up to 1. Okay, and we can write it in the quantum way like this: 0.8 amount on 0 and 0.6 amount on 1. And actually, I can even now explain to you what is this funny weird bracket angle notation. You see, the case of a horizontal photon is not really different. This kind of photon just has x equals 1 and y equals 0. It has all its amplitude on 0. And vertical is, has all its amplitude on 1. So it's y equals 1 and x equals 0. And in fact, when you get down to the mathematics of quantum mechanics, this funny angle bracket 0 literally just stands for this vector, this unit vector 1, 0. And this, funny angle bracket 1 stands literally for this vertical vector 0, 1. And so this actually makes sense. I mean, if you know a little bit about how vectors work, this vector here is literally 0.8 times this vector plus 0.6 times the vertical vector. So the true, way to state it is that like, the state of one logical qubit with real amplitudes is a vector. It's a two-dimensional vector whose tip is on the unit circle. There's another question that says, does it mean we have infinite qubits satisfying x squared plus y squared equals 1? It means that one qubit can have infinitely many different states. Instead of just having two states, it has infinitely many different states. But there's still something kind of two-ish about it, right? If you have one qubit, the two-ish property of it is its true state is a two-dimensional vector. And it's possible to have like more complex particles or multiple particles, and their true states will be like higher dimensional vectors. Vansh Patel asked, can we have negative decimals? Yes, absolutely. All these, and this is very important in quantum computing, all the possibilities on the circle are valid. I've only illustrated this one with like two positive values, x and y, but most certainly you can have negative values for these amounts, which is weird. So like, don't think of them as like probabilities or even like amounts per se. Like it's a mathematical construct, which is just how nature happens to work. It can be a negative amount as well. Okay, so now that we know about like the true state of like what a qubit can be, we can ask how do we operate on these qubits? So now that we realize they have infinitely many possibilities, so if you want to operate on them or compute with them, one more thing you can do is you can shave your slab of quartz to like any thickness kind of you want, and the thickness you make it corresponds to the angle by which it'll rotate if you put the photon through it. These are all obviously all in like ideal physical experimental circumstances. But again, no matter how you have your qubits implemented physically, you can build a physical device that will implement sort of the rotation operation on your qubit state. I'll get to Devashish's question in a second. So yeah, when you pass the photon through a rotate by theta kind of slab, whatever the incoming state is, it'll transform it by rotating its position, or sorry, its angle, if you will, by theta. There's a question, what about a different basis? Right, so actually, I mean, it's a bit arbitrary what the basis is. And the way it really works is, this qubit can have like, infinitely many possibilities on the circle. And we sort of just by convention arbitrarily decide that like, okay, this horizontal axis, we're gonna just call that one 0 or horizontal. And then the perpendicular one, it should be a perpendicular basis. The perpendicular one we'll call 1. But this is like actually just a naming convention. There's also a question, what is the difference between two qubits? I'm not quite sure what the question is. It is true, one thing I'll mention that if you have two qubits, then they have some kind of joint state, which is a 4-dimensional vector. And this is when quantum computing gets really interesting, when you have multiple photons or multiple qubits. But we'll get to that actually not at all in this presentation. I'll stick with one qubit for now. Okay, so just a little bit of math here. That's what we're supposed to be doing, math. If you take the horizontal qubit and apply an operation that rotates it by theta, then what are the x and y? Well, the x is cosine theta, sort of by definition of trigonometry, and the y amplitude is sine of theta. Okay, so we'll like to remember that later. Okay, so now one more question. You see, now that we know we can get a qubit or a photon to have this state, you maybe cosine theta amount of 0 or amplitude of 0 and sine theta amount of 1, at a theta angle. What happens if we put it in the measuring device? You see, this measuring device, again, it exists in physical reality, and it's connected, in my diagram to an LCD screen. And the LCD can only output 0 or 1. Like, if you put this qubit into the measuring device, it doesn't tell you what theta is. There's no like theta business on this screen. It can only say 0 or 1. So what happens when you do this? And I will now tell you the laws of quantum mechanics say what happens. It's maybe the only thing that you could logically imagine if you dreamt about it. It will say 0 or 1 with different probabilities. Okay, so this is like a startling but true fact that we've learned it from physics over the last 100 years. The laws of reality, the laws of physics are probabilistic. Like what happens when you put, this photon that's polarized neither to horizontal nor vertical, but somewhere in between in a superposition into the measuring device, what happens is probabilistic. So it'll still either read out 0 or 1 on the screen. And the probability of it reading out 0 is x squared. And the probability of it reading out 1 is y squared. And this is sensible, like x squared and y squared are non-negative numbers. And by definition, or by the laws, they add up to 1. So this is like a sensible thing for probability to say. Okay, or if it's at angle theta, you would say that the probability of seeing 0 on the screen is cosine theta squared, and seeing 1 on the screen is sine theta squared. Okay, and this is consistent with what I told you before. If the photon is truly horizontal, it's like state 0. That means x is 1 and y is 0. So then there's like a 1 chance, like a 100% chance it'll read out 1. And if you put in a vertically polarized photon, there's a 100% chance it'll read out. I think I said 1 before and I meant 0. It'll read out 1. It's because y is 1 and x is 0. And if you put it in the one that's at 45 degrees, so x and y are both square root of half, then the squares are half and a half. So you'll have a 50-50 chance of seeing either 0 or 1 on the screen. Okay, so I've kind of now told you, in some sense, like all the laws of quantum mechanics or quantum computing that we'll need for doing computation with 1 qubit. I said there's more laws if you get more than 1 qubit involved, but we're going to stick with 1 qubit today. Let's see, I don't see any other questions. If you have any, you might ask. Yeah, otherwise, I'm going to tell you about what you can do with 1 qubit. So I'm going to tell you something called the Elitzer-Weidman-Baum algorithm. This bomb really means a bomb. It's kind of funny. This is like Elitzer and Weidman are physicists. This was from like the 90s or something, and they had an idea for a physical experiment, and they dramatized it by making it involve a hypothetical bomb. They're physicists. They didn't think of this as like an algorithm or a computer science thing, but I'm going to describe it to you as though it were like some kind of algorithm because I want to motivate quantum computing. So, okay, henceforth, here we go, like a 1 qubit algorithm involving a mysterious bomb. So, whoops. Let me get my slide right here. The setup is there's a box. There's a black box. It's opaque. You cannot see inside it, but like maybe a mysterious person has given you this black box, a mysterious and nefarious person. Actually, it doesn't quite look like this. There's a little opening on the side of the box, which is just big enough to fit 1 photon. And actually, if you turn the box around, there's another slit on the opposite side of the box. I can't simultaneously depict them. But there's a slit on both sides, so a photon can like go in and potentially come out of this box. Okay, so let me depict it more transparently. So you don't get to see into the box, but for the purpose of explaining it, we'll see inside the box. And it has the slit on this side here and on this side here. Okay, and this nefarious person who's given it to you has told you there's like one of 2 possibilities. It's a very crazy scenario. Possibility 1, it's a completely empty box. Okay, it's nothing in it, nothing inside the box. Okay. Possibility 2, it's a bomb inside the box, which is kind of weird. Here's my pink bomb here. It's not just any old bomb. It's like a much crazier scenario. It's a bomb where the fuse is attached to a horizontal filter. And it's a weird scenario, I know. But here's how the situation works. You see, if you pass a photon through this box, if the filter like measures it to be horizontal, remember the way a filter actually kind of works is like a combination of like a measuring device, the camera thing that we talked about, and then like an if then else statement. Like kind of first you think of it as like measuring the photon and getting either 0 or 1. And then if it's 0, horizontal, it sort of lets the photon pass through in the horizontal state. And if it's 1, then it blocks the photon and it makes a little bit of heat. And now the thing is attached to a bomb fuse, so we imagine that even if it makes this tiny bit of heat that it gets from blocking 1 photon, then this heat will like light the fuse and like set off the bomb. So there's the strange scenario. It's either an empty box or it's like this horizontal filter attached to a bomb, which causes an explosion if the horizontal filter measures the incoming photon to be vertical. Okay, so strange scenario, but you're given this box, and now you want to decide, is it empty or does it have the bomb inside it? Okay, so yeah, I'm going to sort of try to imagine, it's kind of a little bit weird, but like think of this as like computer code. So like the mystery box is kind of like a function that takes in a qubits. And you can think of it working like this. The filters first measures the qubits and gets back 0 or 1. And this is according to that, x squared and y squared rules business. And if the readout is 0, so if it measures it to be horizontal, then it like passes it through. So like out comes a horizontally polarized photon. And if the readout is a 1, then the box explodes. Okay, so and also if the box is empty, you can think of it like like this, like it takes in a qubit and it just like passes the qubit through the end. So it's one of these two possibilities is the implementation of the mystery box. Oh, somebody asked, just curious, what programming language are you using here? We're not using any real programming language here. This is pseudocode. It's a made-up language that I hope you can understand. I guess it's slightly modeled after the syntax of Python, but it's not really like the syntax of Python. It's a made-up computer programming language. Okay. Now imagine we didn't know anything about quantum bits, qubits. We only knew about zeros and ones, or like we only knew that you could have a horizontally or vertically polarized photon. Then I want to tell you, if you just have this one classical bit, then you can't do anything. You will be very unhappy about this box scenario. Because what are you going to do? You can only do one of two things. You can put 0 into the box, horizontal into the box, but this is not very good because you gain no information. If the box is empty, you put a 0 in, a 0 comes out. If the box contains the bomb, same thing. You put a 0 in, there's a 100% chance it'll be measured to 0, and then it'll just come out. So in both cases, just 100% chance 0 comes out. So you gain no information. On the other hand, you could put a 1 in, but this is a very bad idea because, well, if the box contains a bomb, you will explode with 100% probability. So this is considered very bad. But let's take advantage now of superpositions, or the ability to, have a quantum bit. Have this box, operate on superposition of bits. So this is going to be some code that we're going to try to do, which is like more sophisticated. I, put it here as like hypothetical code. It actually corresponds to some physical thing you can do in physical reality to interact with this crazy box. This will not even be its final form. There's going to be like a better version of this code later, but this will be like a nice warm-up version of the code. Okay, so how does this work? So you see, the first thing we're going to do is like initialize a qubit to 0, or get out a horizontally polarized photon. And then the next thing we're going to do is rotate it by 45 degrees. Okay, I was like all mathy, like I'm going to work in radians. So this pi over 4 radians is 45 degrees. So we get out our piece of quartz or whatever, and great. So now we have an equal superposition of 0 and 1, and then we put it into the box. Okay, and to understand what happens, I'm going to like imagine at first that we have like the empty box. We're going to like consider the box with the bomb in it later. So, okay, if we put it through the empty box, then of course nothing happens. It doesn't change its state, and it just comes out at 45-degree angle. By the way, remember, we cannot like apprehend the state of the photon by like looking at it or something. The only way you can tell like what's going on with the state of a particle, a photon, is with measuring devices. Okay, that was a little aside. The next step of the algorithm here on line 5 is we're going to do another rotation. So we're going to have like another piece of quartz here. Okay, and if the box were empty, then at this point, the photon would be vertically polarized, exactly 90 degrees. And then we're going to put it into the measuring device. And ta-da! In this case, the empty box, there's a 100% chance the readout will say 1 because it's coming in vertical. Okay, so we'll skip to this line here. And our, our program will print out inconclusive, which might look a little disappointing, but okay. I mean, you can see the algorithm ever only prints out bomb or inconclusive, and okay, at least it didn't print out bomb, so that's good. So the summary of this empty case is that when the box is empty, there's a 100% chance this algorithm, if you will print out inconclusive. Okay. So what about if the box has the bomb in it? Well, let's just simulate the code again and see what happens. Okay, so we go back to the beginning. We set up our qubit horizontal state, and we put it through that quartz, and now it's at 45 degrees, pi over 4 radians. Okay, and we put it into the box. Now, here, one of two things can happen. You see, when you have like an equal superposition going through the horizontal filter, it's kind of like it measures it. And since it's equal, there's a 50% chance it gets measured to vertical and a 50% chance it gets measured to horizontal. So there's two possibilities here. One is that it gets measured to vertical. That's a 50% chance. And that's very bad. In this case, the bomb explodes. But let's rewind time a little bit. And remember that as it's going in, there's also a 50% chance that it'll get measured to horizontal. And then it just passes through. Okay, now, but it's a different. Now it's coming out of the box, horizontal polarization. And the next step of the code is to rotate by 45 degrees. So now it's actually back into equal superposition of horizontal and vertical. It's at this 45-degree angle. And the next line of the code puts it into this measuring device. And so again, we actually have to apply this rule. There'll be like a 50% chance it measures to horizontal, and a 50% chance it measures to vertical. So 50% chance we get a 1 on the readout, in which case we do the else condition and we print inconclusive. And again, maybe that's a little disappointing. But again, if we rewind time, this happens with 25% chance when there's a bomb, because there's a 50% chance of not exploding and a 50% chance that you measure 1. But if we rewind time now, right before we put in the measuring device, there's also a 50% chance it'll get measured to 0. And then if we look at the code, it prints out bomb. And that's kind of good. Like that's correct. We sort of detected in this case that there was a bomb inside the box. And this happens again with 25% chance because there's a 50% chance of not exploding, and then a 50% chance that the measurement outcome was 0. Okay, so the summary of this kind of algorithm, which is not the final version of the algorithm, but it's something, is this. If the box is empty, then there's like a 100% chance the final output will be inconclusive, which is kind of the meh outcome. If the box has the bomb, then there's a 50% chance that you explode, which is certainly bad. And then there's a further 25% chance that your program will output inconclusive, which is also kind of meh. But there's a 25% chance that it'll output, oh, there's a bomb in the box. And this is kind of cool. Like if this one actually happens, you're like, wow, I didn't open the box, but I know the bomb's in there. I know that it's not empty. And I didn't explode, which is nice. Okay, is there any question about that? Okay, there's a question from Drew who says, in general, the coefficients of a state could be complex numbers and not reals. That's correct. In this case, we'll be considering its absolute value. Correct. So, I said that the true state of the quantum qubit is sort of x amount on 0 and plus y amount on 1. Truly, x and y are allowed to be complex. And then the rule is not that x squared plus y squared equals 1, but the correct rule is like absolute value of x or magnitude of x squared plus magnitude of y squared equals 1. Okay, so that is a correct rule in the real case as well, but it's also the correct rule, the truly correct rule in the complex case. Okay, so now Dhruv asks, now it's possible to have two complex tuples with the same point-wise absolute values. Taking this example of a photon, what does it mean? In fact, this can even happen in the case with real amplitudes, as you may have noticed. It's a point I wasn't going to get into because it's a very slippery point, but since Drew brought it up, I'll answer it. You see, one possibility for the photon state is 0.8 horizontal and 0.6 vertical, 0.8 comma 0.6. And we saw if you measure that, there's a 64% chance it'll read out 1 and a 36% chance it'll read out, 0 and a 36% chance it'll read out 1. Another possibility is like negative 0.8 comma negative 0.6. And this actually will have the same probabilities of being read out. 64% chance of 0, because negative 0.8 squared is 64%, and 36% chance of 1, because negative 0.6 squared is 0.36. So this measuring device cannot tell the difference between these two states. They all have the same behavior if you give it either this state or the negative of that state. Now, in some cases, it'll also give you the same, outcome probabilities if you negated one of them, if it's like 0.8 comma negative 0.6. Now, actually, there is a different kind of measuring device you can build that will tell the difference between these two states. Well, this state and the reflected state. But actually, this is a very technical point. There's actually no physical device that can tell the difference between 0.8 comma 0.6 and negative 0.8 comma negative 0.6. And so actually, mathematically, it's a technical point, but these are actually really the same state. So even the better representation of the true state is like a line through the origin. It's like a complex line through the origin is like the real mathematical definition of a quantum bit. But let's say you won't go wrong if you just think of it as like any point on the unit circle. But it is true that certain points on the unit circle actually can't be distinguished by measuring devices. Okay, there's another question. Are we glossing over conditional probabilities because a priori we're assuming there's a bomb? Yeah, this is a subtle point. I am not assuming any probability distribution on whether the box is empty or whether it contains a bomb. I would just like to analyze separately, without any probability, what happens if there's an empty box. And there will be some probability aspect to the component because it has a measuring device, which is probabilistic. And separately, if you have the bomb in the box, what happens? And there are going to be some probabilities in that case as well. Okay, let me go on to the final version of the algorithm. So this is okay, but there's a better version. So here is our old code, if you will, or physical experiment. Put it down here. This is the new version. It's got a loop in it. Actually, we'll take a little look at it. We still have the box. The first thing it does is ask the user, or you decide yourself on a sort of safety level, which is going to be a positive integer, n. So you get to choose n. And then the code initializes the qubit horizontally. And mathematically, it defines this angle theta, which is 90 degrees divided by n, or in radians, pi over 2 over n. So this is a small angle, and the bigger n is, the smaller the angle is. Then we have a loop. We're going to do something n times. And what are we going to do n times? We're going to rotate the qubit a little bit by this theta, and then put it into the box. And then we're going to repeat this a bunch of times. We're going to rotate a little bit, put it into the box. Rotate the qubit a little bit, put it into the box. And so this is our rotation device. Now we need to keep the same qubit. So we're going to put some mirrors here so that once it comes out the end of the box, we'll bounce it around back to the beginning of the box, or to the beginning of the loop. Okay, and then after n repetitions of the loop, we're going to read it out, and then it's the same if then else statement about bomb. Or actually now we're going to print empty, not inconclusive. Okay, so let's imagine simulating this algorithm, if you will, or this physics experiment. And first we'll imagine again the empty box. I see there's a question about aliens in the chat. Let me get to that after I show what happens with the code. Okay, there's a measuring device, so let's put the measuring device at the end as well. Okay, so empty box, we're doing this loop. So iteration number 1, we rotate it by this little amount, theta, and then we put it into the box. And the box is empty, so it comes out in the exact same state that it went in as, namely rotated by theta. And then we got to do the second iteration of the loop. So we bounce this qubit back around to the beginning. And on the second iteration, we rotate again. Okay, and now it rotates it a little bit more. Now it's at angle 2 theta. And then we put it through the box, but the box is empty, so nothing happens to it. And it comes out at angle 2 theta, and we bounce it around back to the beginning, and we do the third iteration of the loop. And we keep doing this loop, and we're doing this iteration n times. And the rotation amount is 90 degrees divided by n. So in the empty box case, once we finally finish, I think this is this iteration. Okay, now we've done the loop the nth time. And we want to stop the loop. So in our physical reality, we just remove this mirror at the last moment. And then we put this photon into the measuring device. And now a nice thing has happened. You see, it's vertically polarized. So there's a 100% chance that the readout will be 1. So when the box is empty, we're sure to get a 1 at the end of this loop. And you see from this last line, it prints out empty, which is great. That's correct. So, okay, let's understand what happens if the box happens to be the one with the bomb in it. Okay, so we're going to start this algorithm again. We pick some safety level n. We initialize the qubit to horizontal. Theta is 90 degrees over n, or pi over 2n. We're going to do this loop n times. Okay, so we do the first iteration. We rotate it by theta. Now it's at angle theta. And okay, now we put it into the mystery box. And here it's going through a horizontal filter. Now, one good thing is that this angle theta is very small. And so it's almost horizontal. And so there's a very high chance that when it gets measured, it'll get measured to horizontal. And that's the case where the bomb does not explode. And then it'll come out horizontal. And there is some chance that you'll explode. And we'll analyze this mathematically later. But let's just imagine that the high probability event occurs and it comes out and it's horizontal. Actually, now's a good chance to address the aliens question of Aditya, just because I was going to bring up a related thing, which is it's sort of the laws of physics and quantum mechanics that you cannot directly perceive or apprehend, the spin of an electron or the polarization state of a photon or any quantum property without putting it into like a measuring device. And the measuring device, like this filter, changes the state of the particle. So like if the filter sort of measures it to be horizontal, then its new state is horizontal. And if it measures it to be vertical, its new state is vertical. And in this case, then we get an explosion. So in this case, it looks different. You see, when the bomb is in the box, if the photon comes out and you haven't exploded, it's going to be horizontal. Whereas when the box was empty, the first time a photon comes out, its angle is theta. So there is a difference. Well, you cannot just look at it and see the difference. So this is why the algorithm has to do something more complicated. So what does the algorithm actually do? Well, it goes to the second iteration of the loop with the same photon. And we're going to rotate it again. And now it's back to angle theta. Put it in the box again. It's still close to horizontal. So there's still a very high chance it'll just pass through and get snapped back to horizontal. Okay, so it's a bit different now. In the empty case, it was sort of always ticking up its rotation. And in this case, it's always sort of going back and forth, assuming you don't explode, between angle 0 and angle theta. We can do this a bunch of times. Goes through with a very high chance, which we'll analyze in a second. Okay, and the last iteration, you move this mirror and you put it into the measurer, and it's going to be horizontal. If you didn't explode, it's going to be horizontal. And so there will be a 100% chance the readout is 0, meaning horizontal. So this is great too, because then the algorithm prints out bomb, which is correct. So again, let me summarize what we saw with this new 1-qubit quantum algorithm. If the box happens to be empty, then there's a 100% chance that your algorithm will print out empty, which is great. That's correct. And if the box contains the bomb, then, okay, this is a little bit wrong, but in some sense, like there's a 100% chance that you'll print out, like, I detected a bomb, conditioned on you not exploding. So actually, there's some chance that you will explode. But if you don't explode, if you get to the end of the loop, after n iterations, and you're still alive and the photon comes out, then when you measure it, you'll see horizontal and you'll report that there's a bomb. Okay, and again, you don't know the difference. Like after n iterations, you haven't exploded. You still don't know if it's empty or got a bomb in it. But then this last step of putting it into the measuring device tells you which one it was. Okay, so we'll end with some math. We still haven't talked about what is the probability of you exploding. So here we go. Let's work that out. And you may think it's like a funny situation because on one hand, every time you put the photon through in this case, its angle from horizontal is very small. So there's a very low chance that you'll explode. And the angle is smaller and smaller, the bigger you chose the safety parameter n to be. So that seems good. But on the other hand, the bigger you chose n to be, the more times you put it through the box, so the more chances you had to explode. So you might think, well, it's not clear that like making n bigger or smaller is good or bad for me. So let's see. Ooh, there's a long question here. Okay, I'll come to that in a second. Okay, so let's figure out the probability that you explode. Well, the probability you explode at all is at most the probability you explode at time 1 plus the probability you explode at time 2 plus ... up to time n. This is the union bound. If you have the OR of a bunch of events, the probability of the OR of them is at most the sum of the probabilities. And now all these experiments exploding at some time t are the same, right? Because it's just like a theta angle photon going through a horizontal filter in every case. So we can just say this is at most n times the probability of a single explosion. And for this, we need to remember the measurement rules, the probability rules. You see, every time we're putting in this like photon at angle theta, which is supposed to be pretty close to horizontal. And see, the probability of you exploding on this one time, I claim, is sine of theta squared. Because, okay, the horizontal component is cosine theta, the vertical component is sine theta. And as I mentioned, the probability of reading out horizontal is x squared or cosine theta squared. And the probability of reading out 1 or vertical is y squared or sine theta squared. So the bad case, the explosion is reading out vertical, so it's sine theta squared. So there's an upper bound of the probability that you explode, n times sine squared theta. Okay. Now, a little bit of math talk here. You see, let's zoom in on this circle. Sine of theta is this black height, right? That's literally the definition of sine theta. This is a circle of unit radius. This is an angle of theta. So this black height is sine theta. And this pinkish purplish arc length here is theta, because we're working in radians. And this is literally the definition of radians, right? A theta angle in radians, subtends this arc of arc length theta. And I only bring up these two facts to just note that the pink is longer than the black. So this is a general fact about trigonometry. Theta is always at least sine theta. So sine theta is at most theta. So we can further upper bound this explosion probability as n times the square of theta. Now what's theta? It's 90 degrees over n, or we're working in radians, so it's pi over 2 over n. And now you see a very interesting thing happens. The n's don't cancel. It's more interesting than that. So we plug this in. The probability of exploding at all is upper bounded by n times the square of pi over 2 over n all squared. So when we multiply that out, this upper bound is pi squared over 4 over n. We still have an n in the denominator. Okay, and everybody knows pi squared is basically 10, and 10 over 4 is 2.5. So this is at most 2.5 over n. And this is cool because it gets smaller and smaller the bigger you take the safety parameter to be. Okay, so to summarize, with this algorithm, whatever you set n to be, like you set n to be 1,000,000, then your probability of exploding is at most 2.5 in 1,000,000, or I don't know, 0.000, a bunch of O's, 2.5, which is great. And you can make it smaller and smaller by making n bigger and bigger. What is the cost to you? Well, it's time. This is the number of iterations of the loop. Okay, so this is the overall summary. There's the probability of you exploding. You can make as small as you want at the expense of time, how long you do this experiment for. And assuming you don't explode, you have perfect ability to detect without looking inside the box whether it was empty or whether it had a bomb. Okay, so that's the end of this kind of cool algorithm. Let's see, the question seems to be about what if you're trying to store information via the angle? Yeah, this is a good question. You can actually even ask this kind of question with like, you might think like, oh, I can store infinitely many possibilities with one qubit by its angle. Sort of true, but actually this is not an inherently quantum thing, right? You could say like, oh, by positioning a wooden block at like, a certain distance along a meter stick, there's like infinitely many real possibilities for where I position the block. So I can store like an infinitely many decimals by putting a block on a certain position on a meter stick. I mean, sort of true, but maybe sort of not true. Like, I guess it's like an idealization to imagine that like a meter can be infinitely divided in the real world into like any real number. There will always be some experimental error in how accurately you're able to measure it. Another difference with the quantum world is, if you set up a photon at a particular angle, again, you cannot directly perceive this angle. The only way you can kind of gain information about it, if you have like in an unknown polarization state, like it was when it came out of the box and we weren't sure if there was a bomb or not, is by putting it into a measuring device. And this measuring device will give you some very weak amount of information about whether it was 0 or 1 based on the probabilities of it reading out 0 or 1. And so this is another difference. And this second thing has the robustness built in. I mean, okay, if you read out 0 or 1 with probability x squared, maybe your readout device is not perfect. Maybe it'll be only merely really close to x squared and really close to y squared. But what's kind of cool about quantum computation, we won't get into it, but it's all quite robust to this possibility of slight errors in your physical gadgets that are doing the manipulations of the state and the measuring of the state. So I can't really get into it further than that, but it really is, even though it doesn't seem like it, quantum computing is really like digital computing. It's not like analog computing where you're trying to store like real numbers with infinite precision, even though maybe it doesn't look like that at first.
Like I'm suggesting computing in the probability instead of considering just say angle 0 or pi, that is 1 or 0, something like that. We are considering the probability that is maybe the angle is lying in an interval, say pi by 2 to pi by 3, or pi by 2 power n to pi by 2 power n plus 1. So that is the thing. I'm just restricting the angle and then finding the probability that will that increase some algorithmic, bring some algorithmically advantage. Like classical computers are algorithmically same as quantum computers for now, and the only thing we gain from it is the computational complexity part. But instead, if we do something of that sort, can we gain even the algorithmic advantage too. So that is my question.
If I understand your question, yeah, no problem. If I understand your question, somehow not really. I mean, quantum computers can operate on quantum states, which is something that classical computers cannot do, sort of by definition. In the same way, if you have like a classical computer code, it's normally deterministic. And so if you want like your code to like flip a coin, by definition, it cannot do that. But then if you like allow, you're like, okay, into my model, or I have some physical device that lets me, you know, get some RNG, some random coin flips, then your code can flip coins and it can enter the world of probabilistic computing. It's sort of similar with quantum computing. I mean, if you have just a regular old computer, like it cannot process quantum information by definition. But if you have a quantum computer, then it can by definition. So in that sense, a quantum computer is more powerful than in like a fundamental way than a classical one, because it can process quantum information. But if you say like, oh, I'm gonna have a quantum computer, but I'm only gonna try to solve classical problems where like the input is like regular old, you know, zeros and ones, and the output is supposed to be regular old zeros and ones. I'm just gonna try to use quantum computation to get some kind of advantage in the computation. Then there's not fundamentally more you can do with a quantum computer than with a classical computer. There are a few things that you can do much more efficiently with a quantum computer than a classical computer, but there's nothing that you can do in the realm of classical problems or tasks. There's nothing that you can do with a quantum computer that you can't do possibly more slowly with a classical computer. Let me take, I have like 2 more slides. Let me just give these last 2 slides, and then it'll be a great time for questions, because I see there's some other questions there. Okay, so let me just wrap up. This was the end of this 1-qubit algorithm. And okay, to be honest, I presented like an algorithm. To be completely honest, it's more like a party trick that you can do with 1 qubit. It's still not really real computation, but this is kind of like a baby version of like more sophisticated quantum algorithms, like the famous Grover's algorithm due to Love Grover for quantum search. So it's a good warm-up for actual quantum computation. Things, you know, really get interesting if you have maybe 1,000 qubits rather than 1 qubit. And this is not physically a problem. It's not really hard to get 1,000 photons together. I mean, you open up a light bulb, you get like millions and billions of photons. Okay, now engineering, maybe it's tough. You've got to like build like gadgets to manipulate and separate 1,000 photons. And actually, they're a little hard to handle. They don't like to stay still. So people who are actually trying to build quantum computers don't use photons and polarization for the most part, but they use other properties of small particles, of which it's not hard to get 1,000 of them. It's a little hard to manipulate them. But this is where quantum computing gets really cool, when you have 1,000 qubits. So we won't get a chance to get into it now. But let me just tell you one like little fact about it, which is maybe give you a sense of why it could be very powerful. You see, if you have 1 qubit, its state, as we saw, it looks like this. So it's basically got defined by 2 real numbers, or 2 complex numbers, x and y. If you have 2 photons, you know, if you have 2 bits, they can be in one of 4 states: 0, 0, 0, 1, 1, 0, or 1, 1. But it's the laws of quantum mechanics say actually 2 photons jointly can be in any superposition of those 4 possibilities. And therefore, the true state of 2 photons polarization is like 4 numbers, or like a 4-dimensional vector. And if you have 3 photons together, their joint state is defined by 8 numbers. And if you have 4 photons together, their joint state is defined by 16 numbers. And if you have 5 photons together, the joint state is defined by 32 numbers. And if you have 1,000 photons together, which is certainly possible in physical reality, their true joint state, which is sort of kept track of by nature, is indeed, as Vanch says, 2 to the 1,000 possible numbers. And if you do physical operations to these 1,000 photons, their state changes, and these 2 to the 1,000 numbers change. And so if you can just do some very carefully designed operations to cause the state to change in a very sophisticated way, then it's almost like, you know, you're getting nature to do a computation on 2 to the 1,000 numbers for you, which is amazing. Now, it's not so awesome as you might think, because you know, you cannot just directly perceive these numbers. You can only take these 1,000 photons and put them into measuring devices, and you'll get some probabilistic readouts that have something to do with what these 2 to the 1,000 numbers are. So you really need some quantum algorithm designing smarts to take advantage of this, but it does seem to be possible. So this is the potential advantage of quantum computation is 2 to the 1,000, you know, possibilities, is what makes it all possible. So that's the end of my talk. Sorry for going a little bit over time, but I have plenty of time now to answer your questions. So I'll do that now. Ideally, I have the ability to like fade out this music as well. But you have to enjoy it for a moment and then have a hard stop. All right. Great. Okay, so there's a few questions in the chat. So maybe shall I just address them? Is this a good idea?
Yes, sure.
Okay, great. So let's see. Aditya asks, technically more measurement we do, probability of getting upspin or downspin or both will not be the same, and then we'll converge to classical computations, or will we see the uncertainty? I'm not sure I fully understand the question, but it does bring to mind another question that is often asked, and maybe it's your question, which is this. You see, it would be really great if you're like operating on qubits, if you could just find out what their state is. See if I can get like a good example back here. Okay, for example, here, this qubit, maybe its state happens to be horizontal, but we don't know that. If the box were empty, it might be a vertical or at a different angle. And it'd be great if you could just somehow read out what this state was. Particularly, as I said, if you have like 5 photons together or 1,000 photons together, their state is 2 to the 1,000 numbers. So if you could just somehow ask the 1,000 photons, like, please tell me, this particular number that defines your state, that would be amazing. But we cannot do that. As I said, we can only measure it. And there's these probabilistic rules about measuring. And it's a little worse than even you might hope, which is that when you measure a photon or any particle, not only does it sort of read out either just 0 or 1, but it changes the state of the photon to whatever the readout was. So it's a bit funny with the filter because they like measure and then either make heat or not, depending on whether it's the readout was 0 or 1. But in general, you can even have a slit at the back of this camera and like the photon will come out of it, but it'll come out in exactly the state that was on the readout. And therefore, like you cannot like try to measure it again to gain more information about what, let's say, the angle theta was. You can measure it one time and that sort of ruins it or collapses the state to whatever the readout was. And so if you measure it and it reads out 0, then if you put it back into the measuring device, it'll 100% chance say 0. So you would feel that like, oh, if I could just repeatedly measure the same qubits and rewind time or whatever, I would gain information about what the state was, but unfortunately you cannot do that. Let's see. Debashish asks, will it be a Poisson random variable for larger n? Not sure. Oh, maybe it was like anticipating what would happen with the calculation here. So the funny thing is like, the amazing thing that happened was this square that's inherent in the laws of quantum computation. We did like n experiments, and they are like actually independent from a probabilistic point of view. But the probability of one bad event happening turned out to be like 1 over n squared, or actually 2.5 over n squared. And so therefore, if you do n experiments, each having a 2.5 over n squared chance of a bad event, it's very unlikely you'll get any bad event. We upper bounded it by 2.5 over n. Actually, you can be perfectly careful. I mean, these are independent, so it's going to be like 1 minus sine squared theta all to the power of capital N. This is exactly the probability of not exploding. Nth power of 1 minus, well, I guess it's like nth power of cosine theta squared. So this actually was just some arithmetic in order to like simplify that exact answer to a more reasonable quantity. So if it were true that the probability was more on the order of 1 over n of a single explosion, and you do the n events independently, and each one has around a 1 over n chance of happening, then indeed the number of bad occurrences is like a Poisson random variable for large n. But luckily, that doesn't happen here. If it were like a Poisson, then we'd have like a constant chance probably of exploding. But here we have a very small chance. Let's see, this last question is, photons are indistinguishable. Is the counting right? Yeah, it is the case. Maybe it's the fermions that are indistinguishable. This is getting into some like nation of physics. So electrons are indistinguishable, and therefore if you have like n of them, it's maybe not correct that you have 2 to the n possibilities. But bosons. Somebody back me up. my physics knowledge. For bosons, which I think photons are, it's like 2 to the n. Let's see. Sheffield asks, what is quantum machine learning? Interesting question. A lot of people hope that if we build quantum computers, which seems like we will pretty soon. 10 years ago, it looked like a very difficult engineering problem, but then they got pretty good at it seemingly over the last year. So hopefully we'll build them soon. A lot of people have this hope that if we build quantum computers, then they'll allow us to solve the good old classical problems that we cared about solving, maybe way faster or like exponentially more fast. And there are some early successes that make quantum computing famous, like exponentially faster algorithm for factoring integers. It's a sort of sad fact, though, that after about like 25 years of research into quantum algorithms, there haven't been really too many successes in terms of taking a classical problem that we used to try to solve with classical computers and showing that we have like an exponential speed up or advantage solving it with quantum computers. My take on that actually is that's fine. And perhaps the most interesting applications or outcomes of quantum computing, besides this factoring algorithm and maybe 1 or 2 other algorithms, will be computations that have to do with quantum data. This thing that like inherently classical computers cannot do, like understanding what is the ground state of a molecular structure. This is like an inherently quantum problem, and perhaps quantum computers can solve this problem really efficiently, whereas classical computers cannot. But still, people are still very hopeful that perhaps you'll find some classical problems that quantum computers can solve super efficiently. And people are also really into machine learning these days. And so people like to combine the two. Like maybe we can find some machine learning problems that quantum computers can solve super efficiently. So many people work on this, and there are some arguably positive results. They're sort of at the level of extreme basic linear algebra. So in some arguably contrived setup, you can solve some linear algebra problem, like solving AX equals B, exponentially more efficiently with a quantum algorithm than with a classical algorithm. And since machine learning often uses linear algebra techniques, maybe this is good. That said, it's still like a quantum, sort of a contrived setup. It's not like, you're just given A and X and you got to compute A times X, A being a matrix and X being a vector. There's more caveats than that. So whether this will come to great fruition is maybe still remains to be seen. But I personally am most interested in sort of quantum computing for quantum applications and quantum information theory. Let's see, Aditya asks, can quantum and repetitive state be prepared initially, and after time evolution, we see a pattern and predict the state? This is, okay, great question. This is arguably a different definition of what is quantum machine learning. And this is the kind of quantum machine learning, if you like, that I'm very interested in myself. And this is the question of like, can you learn quantum data? So this is, as I said, I find it a little bit more interesting when you're trying to solve an inherently quantum problem using a quantum computer. Imagine you have some kind of quantum data and you want to like learn some stuff about it. What's the status of this problem? And here you're hoping that maybe you can do it and it won't be much less efficient than the natural analogous classical problems. This is what kind of interests me. So what could that mean? I thought of it because of Aditya's question. You see, it's true that like, let's say you have a complicated state, maybe it's many particles and therefore its state is defined by like a high dimensional vector. You would love to just know what is this high dimensional vector. But the only thing you could do is measure these particles, and this gives you like a little bit of probabilistic information about what this high dimensional vector of different amounts was. So you can't really do much. But this is really not that different from the following scenario. I give you a coin that's not a 50-50 probability coin, but it's a coin with like a mystery bias. Maybe it's 80-20, maybe it's 10-90, you don't know. This is like kind of like there's 2 mysterious real numbers that you would like to know. And if I told you you could only flip this coin 1 time, then this would not really help you be able to learn the heads probability and the tails probability. You flip the coin 1 time, maybe it comes up heads, you're like, well, maybe it was biased towards heads, but I don't know. But what you imagine normally is that you can flip this coin like many times, or you have like many copies of this coin and you can flip each of them 1 time. So quantum state is really like a quantum coin that can only be flipped once. This is maybe the difference between a classical coin and a quantum state, a qubit versus a biased coin. They're both defined by like maybe two real numbers that either add up to 1 and their squares add up to 1. But a physical coin you can flip many times. A quantum coin, you can only measure it once, and then it's sort of fixed to the measurement outcome state. But if this quantum particle, like maybe it came out of a physical apparatus that you built, maybe you're trying to build a quantum computer or a quantum circuit or something, and your quantum apparatus like produced a particle in a certain mystery state, you can imagine that maybe you could just run your experiment multiple times and get n copies of the particle, like n particles, each of whose state was some particular mystery state defined by like a mystery x and y. And in this case, you can potentially learn x and y to good accuracy by some algorithm that maybe measures, maybe it does some rotations on them, maybe it does some operations that entangle the photons. We didn't talk about this possibility yet. And there is some like algorithmic design space here about like how you can learn the state, this mystery state of maybe two numbers, assuming you have a bunch of copies of photons, each of which is in this state. So this is sometimes called the quantum tomography problem, and this is something that I've worked on in my research. Let's see, Ativ asks, can you elaborate what is quantum information theory? Is there an analog of Shannon entropy in quantum computing? Yes, there is. It's a great question. In fact, the true way I think about quantum mechanics or the laws of quantum mechanics is as a generalization of probability theory. And this is like quite literally true. So in the regular old macroscopic world, we have things like dice and coins and cards, and you flip a coin physically and you model it using the basic laws of probability, 50% heads, 50% tails, and there's like these notions of an event and a random variable and expectation and conditional expectation and so forth. And all the probabilistic kind of things that happen in the macroscopic world are well modeled by the basic rules of probability, which you've learned in your math classes. But the behavior of these quantum particles is also probabilistic, and it's not governed by the basic rules of probability. It's governed by this generalization of the rules of probability, which is the laws of quantum mechanics. And it predicts how basic particles behave. And the normal laws of probability involving the familiar macroscopic objects are like a strict special case of this more general laws. So the laws of quantum mechanics are literally a generalization of probability, which is kind of cool. It's like a generalization of probability that applies to real world physical objects. You're just not used to it because you don't normally interact with these teeny tiny objects. And so basically, yeah, you can generalize everything in probability and statistics and everything to quantum versions and quantum probability. And there's even a more general notion of a quantum state beyond the one I talked about in this lecture. So I told you that a quantum state is, a qubit is defined by a two-dimensional vector. That's sort of true, but actually the real definition of a quantum state is a probability distribution over vectors, or another mathematical way of writing it is like a certain kind of 2x2 matrix. So again, this is taking us a little bit too far afield, but in this format, there's a rich world of quantum information theory, quantum probability. There's analogs of Shannon entropy, and very mysterious and a lot of unsolved and interesting problems to do with that. Are there more questions? Okay, well, if there are not.
If there are any more questions, then maybe we can send you an email and we can discuss it later.
Sure, sounds fine.
So yeah, I think we can conclude now. So thank you, Professor Ryan O'Donnell, for your fantastic lecture. It was incredible how you started with a real simple life object, a 60 rupees polarization device, and explained the magical properties of quantum computation using just a single qubit, not any multiple qubits. And we all definitely enjoyed the cool bomb algorithm. And for all the participants, if you want to know more about quantum computation, you should definitely visit Professor Ryan O'Donnell's webpage, and there are a great set of lecture notes and lecture videos which you can definitely enjoy. And we will meet next on 20 October for a talk on shapes and geometry of surfaces by Professor Mahan Maharaj of TIFR Mumbai. And thank you once again, Professor Ryan, for accepting our invitation and taking your time to make these slides and delivering a lecture on Sunday morning. Thank you once again.
Thanks very much. It was a real pleasure. Bye, everyone.
Thanks, Ryan. Bye.